Organizing committee for giving this opportunity to share some of our research that we've been working on for the past almost 10 years, I guess. For those of you who haven't visited us yet, we're located in Edmonton, Canada. So we're basically on the western part of Canada and roughly not quite in the middle, but pretty close to the middle of Alberta. And if you come in the wintertime, you can often see some nice aurora borealis. And if you come in the summertime, you can always catch up at one of our national parks, either Jasper or Banff. So our research area, broadly speaking, is typically governed or directed at energy harvesting or storage type materials. And we, of course, use, as this is a global NMR talk, we use NMR and DMP quite heavily to understand some of these finer structural aspects in these. What we're going to mainly focus on today is bulk semiconductors. We're not going to look much at alternative sources, but the key thing is these are typically identified as perovskite-like systems, and they're of interest for potential solar cell applications. You might be familiar with this, and you may not, but the reason why we were attracted to this about 10 years ago is when you start looking at these metal halide systems, in particular, these perovskite systems where you have a cube-octahedral system with 8 B sites at the corners, and then you have an A site sitting in the cube-octal void. You have quite a degree of synthetic variability, as also as elemental variability that you can basically plug into these systems. And so you can get quite a few different structures and quite a few interesting chemical modifications can result in a variety of physical property changes, whether it's optical or electronic based sources. The other thing that's kind of neat about these systems is when you go to the metal halide series, the A sites can be either inorganic, so this is a cesium cation, for example, or you can add an organic cation such as methyl ammonium or photodetectors into these systems. And so I kind of like to think of it as a spice cabinet, where if you look at the periodic table, you have a high degree of variability. Now, amongst that, you can go even further, and you can go into what are called perovskite-like structures, such as 2D perovskites, where you have these sheet layers, or you have these 0D like perovskites where you basically have these isolated octahedral systems. Vacancy ordered-like systems where you knock out the second B site, or you have these double perovskites. And so again, by controlling not only the elemental aspects, but also the chemistry and the stoichiometry of these things, you can get a variety of different materials. And then finally, if bulk is not what you want and you want to go to the nano, again, you can reduce these systems here and basically trap them as they grow using some type of surfactant to basically functionalize the surfaces, and you get nano perovskite-like phases in the ABX3 things. For most of the talk today, we'll be focusing heavily on what we call bulk 3D perovskites. And the reason why we use NMR for this, if you will, is if you look at these systems, when you start having a crystalline material, but you want to do some slight ion substitutions or modifications, or perhaps elemental mixing, what can happen at times is the atomic structure starts to basically change that may not be able to be readily picked up using traditional diffraction techniques such as X-ray or neutron. And so NMR, because it's sensitive, direct, and isotopic specific, we can really look into the system of these things and understand whether you have a variety of different structure types or phases or what have you that are occurring. It's qualitative and quantitative, as you know, and in this audience, I don't have to go through much aspect of NMR, but really what it is looking at the local and medium range structure of these systems. And then also some variable temperature aspects. So a lot of these systems will form these black materials. And when they're under operating conditions, such as sunlight, they will heat up, and they can heat up anywhere between 60 and 100 degrees Celsius. And so you have to be cognizant of whether or not these changes in temperature will either improve or degrade the performance of these materials over the long term. And then finally, what I think was really fascinating about these systems, which I'll show you a little bit in a few slides, is not only do you have the structural component you have to think about, you also have a lot of dynamic aspects. Okay. And so I'll show you a few examples where not only your A site is moving, but also some of the other elements are moving as well. And so you need something to be able to probe this. And then finally, what's quite intriguing by these materials is depending on the nucleus that you're looking at, you have to at least consider a variety of interactions such as J coupling, dipolar coupling, magnetic shielding, as well as quadrupolar interactions to kind of delineate what's going on in these systems. Specifically, for these ABX3 materials, You can see here in this table, you have a lot of potential probe nuclei that you can look at using NMR spectroscopy. And obviously, proton, carbon, and nitrogen are heavily focused for the hybrid species. Cesium is quite informative, and it's well behaved, if I will say, in terms of a quadrupolar nucleus, because its overall quadrupolar is fairly small. And so you typically get isotropic-like behavior in these systems, whether you're doing slow spinning or moderately fast spinning. For the B site, you have two fairly receptive nuclei, lead and tin, which can be quite informative in terms of the overall structure that happens. And you also notice that these systems, as we go through it, have a fairly large chemical shift range. And so this helps us use this technique to basically identify unique compositions that are forming as you substitute or dope with certain components. Germanium is a little bit more challenging, and I'll show examples of that. And then you have to go basically to the linker. So if you imagine if you have your A site in the middle here and you have two Bs on each corner, you have your halogen nucleus that's basically linking or connecting these systems. And so sometimes this can be useful to identify certain compositions. And so these are the main targets, if you will, that we'll be focusing on over the next 40 or 45 minutes looking at that. Okay. Okay, so I'm going to kind of walk you through a historical perspective of how we kind of got into this over the years, starting with our initial study back when we started looking at 2015, 2016, and then basically to current day where we're still trying to figure out some materials and how to stabilize, we'll say, lead-free systems. So initially, when we started looking at these perovskites, MAPI, which is methyl ammonium lead iodide, was kind of the leading candidate in the 2014 era or so. This is one of the first examples that showed fairly good photoconversion efficiency. It's changed drastically since then, but the basic components are still lead in the center, some type of halogen or a mixture of halogens, then some kind of mixture of A sites. The problem with this is when you start looking at these systems, there was a variety of conflicting reports in this time indicating that the decomposition product of this main perovskite phase was a monohydrate. Some said it was a lead salt, and some said it was as a dihydrate. And I found this is fairly interesting or unique that you get three unique solutions when you're using diffraction techniques. And so I thought, okay, well, NMR is fairly sensitive, and lead NMR should be able to identify what's going on in this case. This is a busy slide. I do apologize for this, but I think it exemplifies why we kind of dived into this more so. What you have is you have the four compositions that you can potentially have. They have the MAPI phase, you have the monohydrate, the dihydrate, and the lead iodide. And you can see that each of them has a unique chemical shift or signature related to them. And only the monohydrate basically has some shielding anisotropy associated with it, where the other ones are basically a Gaussian-like line shape. And so you have a combination of a unique chemical shift for each of these phases that helps to identify what's forming upon degradation. And then you also have to deal with some minor CSA component. Now, in terms of what governs this overall line shape, you do have some dipole coupling between lead and iodine-127, but you also have J coupling. And we've shown, as well as water solution, has shown lead-chlorine J coupling in these systems. And then more recently, Kovalenko groups have shown some lead-bromide J coupling. And so you can imagine that basically this large pattern is comprised of a series of J coupling between the lead and the iodine species. Okay, so that gives rise to the breadth. There is also some T2 considerations because the T2s are quite short in these systems. The other aspect here, if you will, when you go through this is as you heat the sample, you typically have this, sorry, not heated, as you allow humid air to pass over the sample, what we done was we built this humidifying chamber here. We placed this perovskite sample in here and we bubble it through at about 80% relative humidity. And what happens over time is you get this yellow phase, and this yellow phase is the monohydrate phase. And you can see here it occurs over a period of days to about a week. And that basically stays stable. Interestingly enough, if you heat this sample, it will revert back to the perovskite phase, releasing the water molecule. Okay, so that is a reversible process. Now, the only time that this begins to fail, where it's irreversible, is when you start looking at the aspect here of the perovskite phase, and then you heat it and pass humid air over it. Okay, so we heat this to about 360 K, and we pass basic humid air at about 45% relative humidity going across it. Over a period of a few hours to a couple of days, you see the perovskite peak decrease, and you see this lead iodide peak form. And what ends up happening here is the methyl ammonium molecule itself is dynamic and it's fairly labile. And as you heat it, it basically allows it time to leave the actual crystal structure. And then you basically degrade it to excess of iodine and some residual lead iodide, okay? And so this got us to thinking, how can we basically look at ways to stabilize this material and potentially avoid the degradation aspect from this. Subsequently, a few years later, this group out of China demonstrated that if you take your methyl ammonium lead iodide perovskite and place it in soil, the plants will grow, but there's a significant uptake of lead in the into the vegetation. And so this is where we went from there. Okay, so one avenue that you can do this to basically stabilize these systems is you can start mixing A sites and X sites. We chose the opportunity to look at the X sites because with that you can also tailor the basically the band gap of the material by about 2 eV. And so what we looked at is a series of methyl ammonium lead chloride bromide or bromide iodide systems. And what we also wanted to look at here was, again, looking at back at some of the other literature. Depending on the synthetic approach you take, otherwise it's solvent or high temperature or spin coating, hydrothermal, you typically get a different answer in terms of final composition. And this is governed basically by the kinetics and thermodynamics growth of the crystal structure. So this is some work that was done earlier by Abhoy, a previous member of our group. And you can see here, when he took the parent phases of methyl ammonium lead bromide and lead chloride, and he would mix these using different techniques. So if you did a solvent synthesis method, you'd see you get a chlorine-rich phase. If you did it through ball milling or mechanical grinding, you get more of an equal stoichiometric balance of different chemical environments, which I'll talk about shortly. You can see that you can have some type of fluctuation or tailoring, if you will, across the compositional space, depending on what you do. Okay. So let's first explain what these different sites, let's first figure out how these different chemical shifts appear. So this is a chlorine phase here that's apparent. If you add a little bit of bromine, such as 5%, you get this new chemical environment that's forming, and this is just due to the fact that the halogen environment around the lead center has changed to 5 chlorines and 1 bromine. Likewise, if you go the opposite way, if you have a bromine phase here and you add some chlorine, you get this new chemical environment forming here. And so what ends up happening is that the lead chemical shifts are actually quite sensitive to the overall halogen environment. And if you do this carefully over a series of solid solutions and over a series of variable field strengths from 300, in our case, we went from 300 to 900, and you start fitting these data, you can actually delineate distinct chemical shift regions for the different octahedral sites. And you can see that depending on the chemical environments you have and the ratios you can either have a homogeneous or a heterogeneously mixed system. And what I mean by that is you either have statistically, you have random chlorine bromine neighbors, or you have some type of clustering of bromine or chlorine neighbors, depending on the technique that you use. Now, from there, what was kind of fascinating was there were some discussions on not only that the methyl ammonium cation is quite dynamic in that cage, but there was some discussion on whether or not you have halogen migration or dynamics in the system as well. And so what we tried to look at here is looking at lead Xe, and you can see here across the 7 unique compositional spaces here, you have some mixing between neighbors and next nearest neighbors depending on the mixing time. And these are relatively short. We're talking about microsecond to millisecond regime. And what this indicated here is that for the methyl ammonium and the photodetector species, you do get some halogen rearrangement occurring in these systems over the NMR timescale. However, when you put cesium in, this stops. And the idea behind that is cesium is one of the smaller A site cations that you can use to form these perovskite structures. And in fact, when you put the cesium ion in the lead chloride or lead bromide system, you get a slight tilting of the octahedral, and the actual overall unit cell kind of compacts itself. And so we think that this kind of inhibits or limits the ability for this halogen motion, at least on the timescale that we were looking at. Okay, so that kind of summarizes the lead that I want to go into. And from that point on, we really focused our efforts on getting away from lead and looking at other alternatives. So I mentioned to you previously that you can look at 2D, 0D, and double perovskite structures. And we've done a lot of this in the previous time. I've talked a lot about this too, looking at different LED or solar cell type or solar absorbing materials. What I want to present today is some of our other work looking at tin and germanium based systems. and kind of the thought process that we had to go through to try to stabilize these materials. Now, the idea behind here is if we can take lead out of it and replace it with, let's say, tin or germanium, you can then reduce the idea, at least, of the toxicity aspect. The challenge with this, of course, is when you take the lead out, lead's actually the most stable system. Tin has a propensity to basically oxidize. And so if you start off with a tin 2 plus, more often it wants to go to a tin 4 plus oxidation state. So this can be quite challenging to stabilize. And so we kind of focused on that, and that's what I want to share with you today. This is where the frustration meter hits high. This was work done by Michelle Ha, who is another former group member, and she did some really nice work on this. What's fascinating about this particular aspect is we started working on this as we were with the lead degradation study for the monohydrate, but we kept getting different results given the timeframes of running. And what I mean by that is on day one, we get one result, and then later in the week, we get another result for the same compound. So we knew something wasn't stable, and we had to really delineate what was going on during the synthesis process. So the first thing I want to emphasize here is that when you're sourcing your salts, you have to be really careful of screening your starting reagents, because depending on the vendor that you source them from, they may be impure to begin with. And so this is an example of a brand new reagent of tin iodide 2 plus, and that we opened it up and then we ran in the NMR spectrometer, and you can see very clearly that we actually have a mixture of 50-50, even though the vendor says it's 99% tin 2. Okay, so that's the first aspect that you have to consider. The other aspect is when you at least look at the methyl ammonium tin iodide, it's fairly unstable. And so when we be running this material after we make it, we get a variety of different chemical shifts, different line shapes, and it was never really, it was never reproducible. So what we eventually figured out was we'd have to run it as soon as we made it, and we have to do everything in tandem. So what we end up doing is after we synthesize it in the lab in the morning, we take one sample and run it off to X-ray diffraction, and one student will do that. And then Michelle would take the other sample, pack it in an NMR rotor, and run off to the NMR instrument and start recording. And what she realized fairly quickly was even within hours of just recording the NMR spectrum, it started to change, and it changed drastically. And after about a week, you get a very large mess. So something itself is happening, and it's changing. Part of this is explained by the fact that you form a tin 4 plus species. So you form this methyl ammonium tin iodide 6 species. And this is fairly common in the literature, same thing with cesium. So there are some discussions in the literature that you form tin metal, and then a variety of other products that you have. So that's where we had to kind of look at and assess. So one way we shifted from this was to basically look at methyl ammonium, but instead of using an organic cation, we went with an inorganic cation. This should at least stabilize the material long enough that we can actually start looking at it and trying to learn something about it. What you can see here, though, for the chlorine version, is that you have this monoclinic phase, and it goes to a cubic phase as you go up to about 380 K. However, we want to make a solid solution of the cesium tin bromide. The cesium tin bromide species is already cubic at room temperature, and it has kind of an ideal band gap for a tandem type device. Not really relevant in terms of this talk, but that's the goal of why we were looking at it. And so we had to figure out a way to basically form this cubic system and then try to incorporate the chlorine system so that we get a homogeneous single phase solid solution. The way we did this was we took a little bit of the polar plunge, and what we do is we heat the sample to high temperatures, and we quickly cool it down using an ice bath. And this basically creates this metastable state where for at least a week or so, we can play with the material, and it is mainly in the cubic form. Over time, you can see it does go back to the monoclinic form, and we recorded this data in 2020, and you can see that basically over a period of a few months, you basically get this rough half-life of 20 days, if you will. So we can play with it quite a bit. And in the end, what we can do is we can form these really nice solid solution series from these yellow powders to these black powders. This is about a band gap of about 1.8 eV, so it's right in the sweet spot. And you can see here that you get very nice solid solution behavior. And subsequently, not related to this, but indirectly, is now in some of the new solar cell device papers that you'll see from solar cell groups, they're actually using this tin-based perovskite as one of their layers in their multi-junction devices. Now, in terms of the cesium NMR, what we have here is kind of a unique behavior is you don't really see much influence in terms of the different halogen environments. Although we're changing the chemical compositions from a chlorine-rich phase to a bromine-rich phase, you just see this slight oscillation or parabolic shift here that goes back from the beginning. And this is just due to the fact that there's this non-additive effect of nearest to next neighbors. In addition to that, when you look at the tin NMR, you actually get a very different response than you do from the lead. So this is, if you remember, this is the lead NMR, and as you change the halogen environments, you get unique lead octahedral that are representative of different chlorine and bromine chemical environments. In the tin species, you only get one site, and you get a gradual shift from a chlorine-rich phase to a bromine-rich phase, but you only have basically an isotropic peak. And the reason for this, turns out, is due to halogen motion or halogen dynamics rearranging quite rapidly. And in this case, for the cesium tin bromide, we see an activation energy of about 0.3 eV. Subsequently, about a year earlier, Kubicki and Emsley looked at this methyl ammonium tin bromide series and saw a very similar effect in their case as well. And if you actually start going through the literature, you can see here that the tin bromide and the lead iodide and some other tin and lead salts have these fairly similar activation energies with basically halogen dynamics occurring. And so there's discussions on whether these are metallic conductors or ionic conductors. And in this case here, it definitely appears to be some kind of an ionic conductor. I'll get back to this later because we have some new results that are relevant and interesting to this. Okay, one aspect I really like about NMR spectroscopy is always trying to emphasize some of the benefits of it over X-ray diffraction. Although I truly believe diffraction techniques are complementary with NMR, there are some advantages, especially when you're looking at disordered or amorphous systems or nano. So I always talk about degradation, and one of the avenues here we've been trying to emphasize is to try to limit or inhibit degradation. And what you can see here is from using NMR spectroscopy, we can actually now figure out roughly the pathways of how oxidation occurs in these perovskite systems. And so one avenue is you can form this tin 4 plus species. Another thing then you can form is this tin 4 plus with bromine 4 or with cesium bromide as residual. And you can see that each of these have a unique a unique tin chemical shift as well as unique cesium chemical shift that we can use to track these. And what's fascinating about it is using tin NMR is we were actually able to determine there is some residual tin oxide forming. And if you go back to some of the old zeolite papers that we worked on or that the Emsley group worked on, you can see here that there's some nano or amorphous tin oxide forming in this region here that's forming. Subsequently, you also see some cesium tin bromide 6 forming as well. And there is some discussions also about whether you form metallic tin. In our situation with our samples, what we were able to determine, again, looking back at the starting reagents, if you recall a few slides ago, I talked about the problems with the methyl ammonium tin iodide species. If you look at tin bromide, again, from the reagent grade that we source, you can actually see tin metal being present in those samples. And so because we were doing these under solid state conditions, whatever impurities we begin with from our reagents, they just get transcribed through to the end. And so in our particular case, we do see tin metal, but it's not necessarily associated with the degradation of this. It's an impurity from this onset of what we were working with. Okay, so again, if you do solution methods or other techniques, you can probably avoid this, but we were not able to. Okay, so one avenue there is then to stabilize the tin species, and what we have to do is you can either do through halogen mixing, allows you to tune the optical band gap, but it doesn't necessarily stabilize the material from oxidation. So you have to think of it of two other ways. One avenue is you can basically form a solid solution of different B sites. So you can take tin and lead together and mix these, and this is a common approach that's used in the field. But you can see there's a fairly large cation size mismatch across this. And so what can happen sometimes is you might have phase segregation or nanodomains forming. Another thing that you can do that's a little bit more challenging is you can take bismuth 3 plus, which is right beside lead. It's definitely smaller in terms of its overall cationic size, but it's closer to tin. So in theory, you should be able to substitute bismuth for tin, but then it's heterovalent. And so you have to worry about the residual charge on this. And so it has to kick out another material. And so we wanted to know how far we could actually incorporate bismuth and whether or not we can actually maintain the structure and stability. So this is work by Madhu. Madhu just defended last week, and so he's off looking, getting ready to ship out. But this is some of his work he did a couple of years ago. looking at the cesium tin bromide phase and looking at whether or not he can incorporate bismuth. And what you can see here, this is from diffraction at first. You can see here that the parent phase is nice and clean, and you basically see a slight contraction of the unit cell as the bismuth is incorporated. What we noticed also was, depending on the solvent synthesis approach or the high temperature approach, you do see a difference here in the overall unit cell. And so this is kind of interesting that they're technically the same material, but there is a slight difference in its overall crystal structure. Okay, so let's take a look at the NMR. So what you can see here is a combination of cesium NMR, tin NMR, and bismuth NMR. I'll start with the cesium, where you can see that the parent phases agree fairly well for each of them. And then as soon as you incorporate some bismuth, you get this new site that's forming. And we attribute that to basically removing one of the tin species in the corners and replacing it with a heterovalent bismuth, okay? Likewise, for tin, you have this change in chemical shift based on the way you synthesize it, whether it's solvent or high temperature. Again, I'll get back to this, but there's some discussions on whether or not you can basically promote the lone pair on tin. And so the question is do we promote the lone pair in one of these systems over the other? Don't worry about it for right now. I'll get back to that in our last example. What you can see here from bismuth is as you increase the concentration, you basically form these new sites. And again, this is just basically tin next nearest neighbor being associated with either all tin or one bismuth site, or even here, maybe perhaps two bismuth sites. Now, this bismuth spectrum here, I'm not going to emphasize much. It was requested by a reviewer, and we tried, and it was very painful. But I want to emphasize how sensitive the bismuth can be in these particular systems. And so a lot of this work goes based on the fact that if you have a cubic system where your bismuth is sitting in an octahedral environment, you'd expect a fairly narrow line shape. And so what you see here on the edge here with 0.23 and 0.51%, this is in a double perovskite. And what you can actually see is that the line shapes are narrow enough that the octahedral symmetry basically collapses any residual quadrupolar interaction. And you just see actually the bismuth chlorine J coupling in this particular system. On the other end of the spectrum, if you don't have octahedral symmetry, you can have something that will manifest itself into a large second-order quadrupolar line shape. And Sherko has a nice paper back in 2009 that looked at a variety of bismuth compounds, and he estimated it between 0 and over 250 megahertz in terms of CQ. In this particular case, all that we can say is that there's definitely some type of quadrupolar coupling occurring. We can't really fit this or identify it. We also do see a slight shift to higher frequency. And so if you use some qualitative arguments from some oxide chemistry, what you could assess is you're going from an octahedral system to either a distorted octahedral system, such as a Jahn-Teller distortion, or perhaps even a lower coordination environment, such as a 5-coordinate bismuth. And so this is what we think is happening when you incorporate the bismuth species into this material. All right, more importantly, though, is Madhu was able to basically stabilize these materials and maintain the optical properties and structure over a period of a week. So what you can see here is if you look at the parent phase from solvent synthesis, you have this black material when you first start from day one, and then gradually over time, it goes to this gold colored material. And you can also see that the band gap itself also changes from roughly 1.7 eV to about 3 eV. If you incorporate the bismuth to about 10% loading, what you can see is that the NMR doesn't really change much. The material stays fairly constant in terms of its black, and the optical band gap changes by 0.1 eV. And so that by being able to replace a little bit of the tin with bismuth does seem to stabilize the material for a longer run. All right. In my final 10 minutes or so, what I want to describe is some of the more challenging systems we've been working on more recently, and this is to deal with germanium. So now what we're basically doing is we're not only going from lead to tin, but we're going from tin to germanium-2. Again, it has a propensity to oxidize into tin 4+ or to basically germanium oxide. So they're quite challenging to make. But the idea behind this is whether or not we can shrink that D site and maintain some of the tricks we've learned through lead and tin and try to stabilize these materials further. Before we went into this, I wasn't even sure if they would be stable long enough to actually do any NMR experiments on them. And so Riley, who was basically our germanium chemist in the group, who's at TUM now, basically looked at these systems. And I asked him to first try to synthesize just the parent phases to make sure that we can actually maintain them long enough to actually do characterization on them. And he was able to do this, and he has some really nice results from the 900 facility in Ottawa. And what he determined was actually fairly commonly seen in germanium. So if you look at past studies in germanium oxides and by the Craker group, if you look at some germanium studies by the Wong group looking at organic solids, and some of our work looking at chalcogenides and expanding to halides, what you can see is that the germanium overall chemical environment is quite sensitive to basically the polyhedral distortion about it. Okay, and so if you look at the bond length difference between the germanium units and the halogen environment, in the cesium germanium iodide, you basically have almost a perfect octahedron. And so this slight distortion results in a relatively small second order quadrupolar line shape. Remember, germanium is a spin 9.5, so you can get away with quite a bit on this. But it is ultra low gamma. So just in terms of the concept of how difficult this is, if you're operating at 500 megahertz, your probe has to tune to about 12 megahertz. And if you're operating at 900 megahertz, your probe has to operate around 30 to 31 megahertz, depending on the exact frequency. Okay, so these are very low gamma. This is a very low gamma nucleus. You need a lot of material. You need a fairly robust approach to do this. And so we use a variety of echo and CPMG techniques to do this. If you start distorting that germanium bromide polyhedron, you can see that it manifests in a larger quadrupolar coupling constant. This is the central transition, of this system. And likewise, if you go to chlorine, this is the most distorted out of all of them, and you get a CQ of about 34 megahertz, which spans nearly 10,000 ppm and for germanium. Okay, so we can use it. It is sensitive, and we can detect it. We can stabilize them long enough to actually measure. The question now results is their actual performance for the germanium systems is actually quite low. So this is a really nice summary of the progress, if you will, in terms of perovskites. You can see this red line is 3D perovskites with basically dominating by lead, and it's even higher now. I think we're closer to 26% now. So you can see that lead's quite successful. The lead tin mixtures have been fairly good, and they're getting better. These are some of the tin species, and they're still improving. And so the idea behind this is if we can then incorporate some germanium with some tin, can we improve the overall stability of these materials here and potentially start increasing the PCE with these systems instead of them degrading into a variety of byproducts? So this is, again, some work by Riley and some work by Brian, who's taken over, and I'll show this in shortly. What their process was is we do know that the synthetic way we treat them does influence their overall property and stability. We also know that we can stabilize the parent phase of the germanium. And so can we basically further improve this through some tin substitution? Okay, and so basically you make a complete complex series of materials that are fairly robust and do not necessarily degrade and don't really have any direct toxicity concerns when you're thinking about forming a cell. So what you can see here is a combination of diffraction results and some cesium NMR results. And what you can see is you go from this trigonal germanium phase to this cubic tin phase. And in general, you can incorporate the tin into these materials fairly readily at lower ends. And then at some point, it converts back where you basically incorporate small amounts of germanium into these materials that are tin-rich. But you get into this 50-50 frustration here where you basically form two, it looks like two phases or two heterogeneous systems, okay? So that there's this phase immiscibility. So we wanted to look at this a little bit more and see like why we can't push it to one side. What do the properties look like on these systems? So we're going to look at these materials, looking at the parent phases. So this one will always be germanium, this one will always be tin, and this one will always be 50-50. And then we're going to walk through basically the synthetic treatments that we take. HT is high temperature, MCS is mechanochemical, and then SS is solvent synthesis. And what you can see in general is although the X-ray diffraction for the parent phases comes back almost identical for each phase, There is some small variability in the optical properties of them. You have for the germanium, you have about a 0.2 eV change in the overall band gap. And for the tin species, you have about a 0.1, 1.5 eV change over these systems. And then you have this mixture one, which is basically a mess. Okay, there's lots of stuff happening here. And we're not going to talk much about that in terms of the properties, and I'll tell you why shortly. What ends up happening is if you actually look at the cesium NMR, the germanium one is fairly robust with the clear signature for that particular phase. And around 10 ppm over, you can see that the tin species, again, shows fairly reproducible results between the solvent synthesis and mechanochemical synthesis. But if you recall a few slides ago, I said whenever we do the cesium tin bromide system, there's always an odd response to this. And if you look at the cesium NMR, again, you see a slight shift. And so the question is what's going on with this tin phase when you do a high temperature treatment? Likewise, if you do a 50-50 mixture, what you see here is you basically have this phase, separated phase where you have this, tin-rich and germanium-rich species. If you do mechanochemical, you get a little bit better mixing in the overall populations. And then a high temperature, again, you have this asymmetric peak that basically overlaps both of them. And this, I would argue, is still phase separated. So we can't really form a single trigonal or cubic structure with this composition. And the idea behind that is if you look at the microcrystals that we make, if you actually do a line scan through the EDX, what ends up happening is you basically have this interflipping between a germanium-rich phase and then a tin-rich phase, and then a germanium-rich phase, and then a tin-rich phase. And so what I like to think about this is if you're in the environment and we wait thousands of years and basically you're forming a mineral, the ions around allowing that to precipitate out will either be dominated by germanium or tin. So although there is always tin-germanium mixing, the overall phase space, if you will, as the crystal grows, is you'll go into a germanium-rich regime, and then you form a tin-rich regime, and it just oscillates back and forth depending on the composition and what ions are around it. Now, this is kind of a brute force approach looking at germanium NMR. A lot of this was done at 800, and one of them may have been done at 900. But what you can see here is, again, the germanium system, regardless of how you make it, provides, again, robust germanium NMR parameters within errors of each other. This is very similar to the cesium. So unlike the tin series that shows a lot of variability depending on how you make it, the germanium one doesn't really care. It seems to always form the appropriate structure and behaves at least chemically and electronically the same. All right, going on from there, the problem we have is sometimes might want to look at the actual halogen environment, okay? And for the most part, we've been focusing on NMR for all these systems. And there's good reason for it, because you get not only chemical shift to dipolar and J coupling information, you also get quadrupolar information if it's relevant. The problem is for chlorine, bromine, and iodine, although they're all NMR active, you have different challenges associated with them due to their overall quadrupolar moment. Okay, and so what I'm going to emphasize here is not heavily NMR versus NQR, but just some considerations if you're going to do this. And this really builds from a lot of the foundational work done by Bryce's group, looking at a variety of halogen NMR nuclei, and some more recent work in perovskites with Kovalenko's group. So what you can see here is this is bromine. And so we wanted to look at bromine in a variety of these crystal structures. And remember that the cesium tin bromide and the cesium germanium bromide had these unique, the crystal structures may have been changing or slightly expanding depending on the synthetic protocols. The problem with bromine NMR, this is done at 600, is you have two isotopes that are fairly close to one another. They're around the carbon frequency, so you also pick up the copper metal from the coil that we have in the probe. And then you basically have their central transitions overlapping, or they can overlap depending on the system. And this is spanning megahertz, right? So we're at about 25 megahertz here in terms of step frequency. So it's not necessarily really conducive to do this quite easily. If we do some quick DFT calculations just to get an idea of the perovskite space, whether they're 3D perovskites or perovskite-like materials, this is a two-dimensional one and this is a zero-dimensional one. What you can see here is that the chlorine species, these are predicted spectra for the NQR frequency, is quite nice, but they're low frequency, between 0 and 10 megahertz. Okay, so this way suggests that chlorine NMR is still probably
best approach. And obviously, there's a lot of great work by Sherko and Rossini and Bryce and Wasilishyn looking at chlorine NMR and many others. Bromine is kind of the in-between sweet spot. There's some benefit to do the NMR, but there's also some benefit to do the NQR. And most of these resonances for these systems show up between 30 and 58 megahertz in terms of their quadrupolar frequency. And when you get to iodine, I'd basically suggest you default to NQR because the quadrupolar couplings can be quite large. And some of the systems we've done some DFT calculations on even predict that they're upwards to a gigahertz in terms of CQ. Okay, so Riley nonetheless basically tore apart one of our old probes and got a series of capacitors and basically was able to tune it up to basically go through the range that we needed of roughly 60 to 100, or sorry, between 30 and 100 megahertz. And he basically was able to step across these and record both the bromine 79 and bromine 81 NQR frequencies for each chemical, or for each crystalline system. He also, with the help from Victor at the 900 facility, was able to do some bromine NMR and being able to identify the distinct sites between these two crystallographic systems, and of course the 0D system as well. Okay. On the flip side, DeGonta looked at some chlorine NMR on these results, again showing that there is some sensitivity depending on the overall chemical environment. He looked at a whole bunch of perovskite and perovskite-inspired systems and showed that there's a huge degree of versatility and variability in this. And really quickly, what I want to emphasize here is that chlorine NMR, especially when you incorporate some of the ultra-wideline techniques demonstrated by Sherko, at down to 7 Tesla, so this is a 300 megahertz magnet, we can basically detect impurities down to about 5% chlorine, okay? And so if you're trying to look for dopants or impurities in these systems, this might be an attractive approach. Or if you want fairly rapid acquisition of these, you can go to higher fields, 8, 9, maybe a gigahertz, and get them in about 30 minutes. So that's a really nice way to go. For bromine right now, we kind of default to NQR. We find it's a little bit more easily to process and find. The problem is, and I always caution this, is it's not always simple to actually find your signals. So we typically rely on DFT to kind of predict where we should be looking, and then we move it over there. And then NQR, again, there's some nice work by Igor Witkowski as well as Kovalenko's group where they looked at iodine NQR, and that's definitely the way to go for that. Okay, so let's go back to why I did this. Remember this problem we had when we looked at the tin versus the germanium parent phases, and we got these unique results. Again, for the bromine NQR, for the germanium, you basically get fairly similar overall behavior. Obviously, the solvent synthesis has a very nice, highly crystalline sample, whereas the mechanochemical and the high temperature has a little bit more variability, so you have a little bit larger span in terms of the mu Q. But again, when you look at the tin species, you see this unique change in the overall quadrupolar frequency by about 0.2 megahertz. And you also see this change in the signal to noise of the bromine signal as well. And so this is something that suggests maybe that there's some type of electronic, maybe a paramagnet system. And so this drew our attention to try some EPR. And what it appears to be is when you have the high temperature phase, there is some type of unpaired electron present in this situation. And you also see it in terms of the tin NMR, that there's some kind of an interesting effect that's basically shifting the expected chemical shift around minus 250 to around, let's say, minus 700 or so. And there's a little bit more temperature sensitivity on this. So what we're thinking is happening is when we make the cesium tin bromide species at high temperatures, we're either inducing some type of 3+ state or activating this lone pair, and it's making it a little bit more metallic-like in behavior. And this might also relate back to, remember I said that we typically found that these were ionic conductors. However, when we do a high temperature synthesis, if it appears to be a little bit more metallic-like, and this might go back to the previous literature where they're looking at these materials, and there's a lot of discussion on whether they're ionic or metallic conductors. Again, I'm not 100% certain what we're seeing. This is still some newer work, but it is interesting that you have very distinct features that are prominent in the NMR spectra. So I think the take-home message here really is to understand that when you're looking at metal halides, not only do you have to be cognizant of the different chemical compositions that you're inputting, but you also have to think really carefully on how the treatment or the synthetic method is. And so you can imagine it as a spice cabinet of elements, and the way you're going to prepare your meal, you have to be very cognizant that both a synthetic approach as well as the elemental composition can really influence both the structure of these materials as well as the optical, chemical, and physical properties. And so as long as you are cognizant of that, I think we're okay. I hope I demonstrated at least that magnetic resonance provides a fairly robust way of looking at a variety of structure and dynamic questions in these systems. We mainly focus on structure, but there were some times where dynamics does pop up. The germanium, tin, and lead halide perovskites do have some similar trends. Okay, you can imagine this where you do have some halogen rearrangement in the lead as well as the tin. The tin are a little bit faster. If you basically shrink the unit cell size down, this will cause some tilting in the overall octahedral, and it kind of locks in or inhibits some of the dynamics. Cesium, tin, and lead NMR are very sensitive probes to use for this aspect, and they often offer large degrees of chemical shift range. So you can potentially easily identify impurities or different phases or basically composition space depending on what you're doing. Some of the quadruploid-based techniques do help out in certain circumstances. Germanium, looking across different series, is definitely identified of unique compositions. You can use chlorine and bromine to look for dopants and impurities and other aspects of this, as well as overall discussions about symmetry. NQR, I think, is probably the most effective approach forward for bromine or iodine. And this has been shown also by others in the field. And then more importantly, I think across the whole series of these perovskites, when these are in a 2+ oxidation state, they always show an inverse halide dependency, which is pretty dominant by a large paramagnetic contribution to the shielding term. And overall, long-term stability improvements can be made through chemical modification. We're still working on this, and I think the germanium ones will be where we're focused on now, hopefully enough where we can actually make a viable device. With that, I want to thank you, the audience, for listening. Our current team members, a lot of this work was done by Diganta, Madhu, as well as Brian, Abhoy, Michelle, and Riley and Braden throughout the past, I guess, 9, 10 years or so. And I'm happy to take any questions.
Perfect, Vlad. That was really great. We enjoyed your talk, and it was really helpful and insightful. So we've got 2 questions in the Q&A chat box right now. So I'm just going to read it aloud for you. So let's begin. So this first question is from Emily Hiralal, and she says, why doesn't the 19910 day 7 peak show a change in its NMR, even though the phase of the compound is changing?
Oh, I gotta read that.
Yeah, sure.
Good question. Okay, so we'll just rewind here. So you're referring to this one, Emily, right here, I think. Uh-oh, I may have frozen it. Sorry, too many transitions. And
That's okay.
your question, Emily, is this one right here. Why does this peak not change? Okay, so what ends up happening in this particular case, if I remember correctly, and if I'm wrong, Madhu, I apologize. I believe what ended up happening was you still have residual cesium tin bromide. So you have the same chemical shift, but what we don't show you is that way over here, okay, about minus, I think, minus 2000, we also form the cesium 2 tin bromide 6 phase. So we don't actually show that, but if you acquire it over here, you see that. So what ends up happening is this composition decomposes through oxidation, and that's what gives rise to the color change. But you still have some residual tin bromide here. Okay, so I think if I remember correctly, that this one here is yellow. This one here is sorry, the 6th phase is yellow, and this one's black, and so combining together kind of makes it this dark brownish gold color. Okay. Okay, next question's by Jeff Reimer. NQR, yeah. Okay, so mainly the reason why we don't approach it that way, Jeff, is bismuth is in a spin 9/2,
And so if you basically scale it, the quadrupolar frequency, again, I don't know what the CQ is on this site. There might be a variety of business sites in here, but the frequency gets too low for us to actually tune the probe to, so we can't really try it. Not something we like to admit, but we just can't do it. Brian Lucier, you asked this, the observation of J coupling in some of these spectra is interesting. Was there any additional structural or material information yielded from these? No, not really. Unfortunately, not really, Brian. All we do know is that at times, the J coupling is observable, and at times we can try to measure it. I think in this bismuth chloride example, we do mention that in the paper, although I don't recall what exactly it was. But most of the time in our materials, we do not see the J, but we know it's there. I think some of the other work, I'll just highlight some of the Kovalenko work, for example, where they're making really nice crystalline systems or nano systems, and they cool it down. They can often resolve some of these data. What we've noticed is if you do anything other than solvent synthesis, you typically have just enough local disorder that the combination of dipole coupling, small chemical shift changes due to the slight randomness of this kind of blur that resolution factor out, whether you're at low fields or low temperatures. I hope that answers the question. All right, Saddam says, how fast particular pulse sequence evolve? Okay, yeah, so in general, you can do most of these experiments between 10 and 35 kilohertz. So if you're in the chlorine-bromine regime, you can do MAS experiments that are about 20 to 25 kilohertz will work, because the line widths for the bromine systems are typically between 15 and 20. So as long as you go fast enough, it works out okay. For iodine, you typically have to go to about 35, because the iodine line widths, the lead iodine line widths are typically around 26 kilohertz. Okay. When you start doing the mixtures of these solid solutions, depending on what you're seeing, for the lead example I showed earlier, you'd have to spin over 200 kilohertz to actually do MAS spectra. So those are actually done under non-spinning conditions. And so that's the only way you can really approach that, including the XE data. The XE data are actually done under non-spinning conditions. So I hope that kind of answers that question. In terms of pulse sequences, you can the typical ones we rely upon are typically echo, either a CPMG or worse CPMG approach, XE. If you have protons around, or you can use something that's a high gamma nucleus, we do cross polarization or het core based experiments. But for the bulk of them, they're pretty much one-dimensional type, typical hot echo, solid echo, CPMG or worst CPMG to do most of these. Okay. Marvin, hey Marvin, how's it going? How far can you get in this kind of work with standard HX or HXY commercial probes? Okay, so standard HX or HXY commercial probes, all this work can be fairly readily done with an HX probe. What I mean by that is nitrogen to phosphorus tuning range. Lead can be done, the tin can be done, cesium can be done, all those types, including the bismuth here that we used. The only time that we had to kind of go to a specialized probe is some of the variable temperature work we've done, which I didn't show you in this talk, but we've had to go to about 600 degrees Celsius in one case. And so that one we use a laser probe to heat the sample. It is commercially available, but it's unique in that sense. And then the other one that would be different is when we did the germanium data, our tuning frequencies, I think on the 800 was around 27, 28 megahertz at 800. So you'd have to get a low gamma probe. And I won't say much more in case there's commercial representatives, but we had to kind of argue to get that probe because they said the sensitivity would not be good enough. But it works out decently well in the end. So I hope that answers your question. HXY, I didn't show any of the data that we've done on some nanoparticles.
We have done some reador experiments, so we have tuned it to proton, cesium, lead, and phosphorus in terms of the HXY. Okay, Ping Yu, for those heavy metal samples, do you need to dilute them with some light materials to spin up safely? In these particular samples, we don't normally need to dilute them. They usually behave fairly well. They are semiconducting, so we haven't had too many problems with them in terms of spinning up safely and robustly. You can see, I'll just give you a hint, we did do a thermometer, NMR thermometer paper years ago, where if you take methyl ammonium lead chloride, you do see the chemical shift of the lead peak move about a ppm per degree. And so you do get frictional heating on the sample, but that doesn't necessarily influence, it does not necessarily influence your ability. I will caution you though, if you start getting into semiconducting materials that are really low band gap, so let's say below 0.6, 0.7 EV, that's where we typically notice, or you get into metallics, that's where we typically notice a problem. And then so what we'll often do is we'll dilute the samples, usually with dry silica is what we normally go to, but there's a variety of samples you can't. So that will help you spin the sample and kind of maintain stability. Okay. Okay, this is from Larissa. Thanks a lot. Very good. Even though you do not see an EPR signal of the sample, you do see a slight shift as compared to the solvent synthesis. Can it be due to differences in the background hole density? Also was the methyl tin iodide NMR rotor that showed fast degradation closed in nitrogen. Okay, I'm gonna answer the second question first because the other question is a little challenging, I think, to address. So in terms of the methyl ammonium tin iodide rotor, in terms of fast degradation, yeah. So the interesting thing about this is probably the only time that I've ran a sample that would not be stable during the experiment. And so what I mean by that is the rotor was ran under a closed nitrogen environment. We actually have a nitrogen generation unit in our facility. And so we use nitrogen push gas for all MAS experiments. And it's usually about 99% or higher. And it's pure enough to run DNP without freezing up. So I'm not exactly sure why the degradation would happen so quickly in a relatively sealed NMR rotor. But in this particular case, it did break down rapidly. What's interesting, though, I will mention is we don't think it's oxidizing in that particular circumstance. So we don't actually see tin oxide forming. I don't know what's forming. I have never been able to figure out what exactly that really broad 4,000 ppm chemical shift range blob is. But it's definitely moving towards the metallic side of tin. But again, it's still far away from metallic tin, so I'm not sure what it is exactly. But it's not necessarily forming an oxide per se. In terms of the hole density and so forth, this is something that we've thought about, but it's actually quite challenging to look at. So some of the things we wanted to do was basically look at. I'm blanking on the technique. We have a group in physics that does a lot of semiconductor testing to look at basically how the materials behave under different conditions. The issue is this particular group often needs a single crystal, or they need the ability to make a thin film. And when you start doing these different treatments, whether it's solvent synthesis or mechanochemical synthesis or high temperature, we often get powders or crystallite, large crystallites. And so they can't necessarily analyze the hole densities. So I can't answer that question, but it's definitely possible.
Okay, perfect, Vlad. Thank you for all your answers. I don't really see any more questions popping up on the chat. I just have 2 questions over here before ending the session really quick. So since you have the slide open here, on the bismuth spectrum here, like I was wanting to know, was there any kind of, calculations done on the NMR parameters to kind of extract the CQs or, kind of addressing as to how broad in terms of, the spectrum was in megahertz?
No, we didn't do any calculations in terms of the. So one of the problems with this is no one actually knows the chemical environment of bismuth, whether it's 6 coordinate, 5 coordinate, 4 coordinate. We're not really sure what. There's a lot of debate on this, and so from a theoretical aspect, I guess we could have done some cluster calculations and looked at different chemical environments. But I think as this earlier work by Sherko did quite a bit of work in this different space. The quadrupolar couplings can be quite large, and so all we do know is that it's no longer in that octahedral symmetry, right? That the tin is sitting in. Okay, so we know the tin from the crystal structure is octahedral symmetry, but we know that the bismuth is no longer that. And so we didn't do anything further in terms of estimating it. The other thing I worry about, which we always have to be concerned with, there's a lot of reports that you can load up to 20 to 25% bismuth. What we learned from this study was once you go past 15, you actually start forming bismuth side products, as well as there's evidence of bismuth clustering. And so by just gaining this spectrum, the only thing it can tell us is that it's not octahedral, right? I don't know if we have 2 different bismuth sites. I don't know if we have, there's the chance that there might be some residual bismuth compound that we can't identify. And so I didn't really want to go too much into it, considering the fact that it was a reviewer 3 question. And if I can clearly answer a question from the data, I'll take a stab at it. But if it's not clear, I leave it up to future work, right? Can we do better in the future? Yeah. With a lot of that work, I think Brooker released a 1.3 gigahertz, and we have the 1.5 gigahertz in Tallahassee. Those might be the future questions that you can attack, right? Because that's where high field work would definitely help.
Yeah,
in this
absolutely. Yeah. And the last question before ending our session, I just wanted to ask you, so for these kind of materials, right, like the semiconducting ones, like how do I know, they're kind of, like stable, like once packing in the rotor, are there any like caution to be kept in mind, because they could be sensitive? So are there any like cautionary ways or something
Yeah, so
from the
like
experiments? Yeah.
one of the benefits is there's now like they're colorful. I hate using color as the tool, because there's plenty of times where I tell my group don't use color to think that it's right, and sure enough it's not. But typically speaking, when you have the black material, that's usually the iodine rich system or a bromine rich system, they will change color quite readily once they start to react, right? And so that's kind of your first hint. The other thing is the lead compounds are fairly stable, and they're long-term stability. So you can make them, and they're fairly robust. They might pick up water, but you can usually cook the water off. And there's also enough literature, I think, out there now in these particular systems that kind of identifies which ones are problematic, and the ones that are problematic are the lighter element ones, right? Like germanium and tin are really problematic. But we're figuring out strategies to stabilize them. I think also again, we don't really do the material device testing. We've tried once or twice, and we weren't successful in the germanium systems, at least. But one of the things we got to remember is, from an engineering side, if you can stabilize the material long enough to get it into a device, you can usually use other techniques such as polymer coatings or other aspects that will basically inhibit further breakdown. Okay. The other thing too that you have to be cognizant of is sometimes it's not a chemical degradation. In the methyl ammonium lead iodide case, I didn't show this part, but we also did some SEM images of a film, and what ends up happening is, as you temperature cycle this, so those black solar cells, they operate at about 80 degrees Celsius, right? So as the sun comes up, they'll heat up, and then as the sun goes down, they'll cool down. And so at least in Canada, right, where you're at minus 30, like the temperature swings of these materials can be well over 100 degrees, okay? And what ends up happening is you actually get micro cracks. So from the device performance, it actually breaks down because of these micro cracks, not necessarily oxidation, right? So yeah, I guess in a nutshell, look at color, and then and then look at NMR, and do a search on the literature, and you'll pretty much find whether they're stable or not stable, and that's how we go about it.